So just a quick recap of synthetic division. I'll show you an example of it in just a moment. Synthetic division is a way to divide polynomials. Sounds good, but really, we're going to use it to factor polynomials. That's going to kind of be our purpose here. That's going to be our purpose. So with that in mind, real quick, let's define a polynomial. Polynomial is a function which fits the following form. F of x, so it's a function, so we can use function notation. And this is going to look weird at first, but I'll kind of show you that it's really not as bad as it looks. I need a little more room than that. So let me shift everything over.
A sub n at the end.
So this is the basic form of a polynomial. And all it's saying is that x is your variable. And so it's just saying it's some combination of this. These a things are the coefficients of your different variables. N must be a positive integer. Each coefficient must be a real number. So it restricts the different kinds of things you can have. N must be a positive integer and is called the degree of the polynomial. So of course, let's look at a couple of examples of things that are polynomials and what their degree is, and also things that are not polynomials. Are and are not polynomials. And this is just kind of a preamble to section 3.3 here that we'll be starting today. Examples of polynomials. Over here will be examples of non-polynomials. So how about f of x equals 14x cubed plus 7x squared minus 2x plus 1. This is indeed a polynomial. The reason is that look at all the powers of x's. One of the subtle implications behind that definition I just did was that all the powers of x's have to be positive integers. So here you have a third power, which is fine, a second power, a first power, even though it's not written, and then you can also have a constant thrown into the mix, just a single number with no variable attached. That's going to make it a polynomial with degree, the degree is the highest power you see, 3. We'll also define a term called the lead coefficient, and that is the coefficient of the highest powered term, and that's clearly going to be 14 here. One thing to be wary of, lead coefficient doesn't always mean it's at the beginning. It'll be at the beginning if you write the polynomial in proper descending order. But if you don't, the lead coefficient doesn't have to be the first one. It's whatever coefficient is attached to the highest powered term. And just to drive that point home, let's look at another example. Negative 1/5 x to the 5th plus the square root of 2, but then the square root ends, times x to the 17th power. Once again, this is a polynomial. All the powers of x's that you see here and here are positive whole numbers, positive integers. You don't have any 5.5 power, no negative powers, nothing weird like that going on. It is a polynomial. It's going to have a degree. Now it's 17. It's the highest power you see, not the first power you see. And then the lead coefficient is going to be actually the square root of 2. It's not the first one you see, but it's the one that's attached to the highest powered term. So lead coefficient is square root 2. Now, what we're going to see when I go to some examples of non-polynomials is that the square root of 2 is okay as a coefficient because square root of 2 is still a real number. That's still a real number. Negative 1/5 is still a real number. So the coefficients of these things don't have to be positive whole numbers. They have, some of them happen to be here, but in general, that doesn't have to be the case at all. It's just that the powers of x can't be anything funky. Those have to behave well. But the coefficients can be a little bit more relaxed. They can be any real number. So in that case, let's look at a couple examples of non-polynomials. Non-polynomials, they may still be functions, but these are not going to be polynomials. 1/6 x to the 4th, that doesn't bother me so much. Minus 3x cubed, everything's looking okay so far, plus 4 square roots of x. Oh, that's going to be a problem. That's going to be a problem. This is not causing any issues. That still looks fine. This is not causing any issues. It's the square root of x here that's going to cause issues. The square root is equivalent to a 1/2 power. So the square root of x can really, you can rewrite that in a completely equivalent form as x to the 1/2 power. And now this doesn't behave properly. Now, writing x to the 1/2 power, you've introduced your variable. Whoa, just move it. You've introduced your variable x, and now it no longer has a nice positive whole number power. 1/2 is certainly not a whole number. So that is going to make it fail to be a proper polynomial. Now, that doesn't mean it's not a function. It's actually still a function, and there's still things you can do with it, but it's going to fail to be a polynomial. Notice here the square root was just on the coefficient, the square root of 2. That's okay, because that's still just a real number here. You just can't attach it as the power of x. Let's see another example. How about negative pi x to the 91st power minus 17 over x to the 5th plus 4x to the fifth power. Let's analyze it piece by piece. This term is actually a-okay. X is being raised to a positive whole number, 91, while it's a big nasty number. 91 is still a whole number. And its coefficient of negative pi is still a real number. So the coefficient and the power on x check out. So this term is actually totally fine. This term does not break it from being a polynomial. This term is clearly also fine, the 4x to the fifth. There's no issues there. That's just 4 is the coefficient, it's a real number. 5 is the power on x, good to go. But here, by dividing by x to the fifth, you've entered into the twilight zone. You've created some problems here. Because when your variable's on bottom like this, or anytime you're dividing by something, you can bring it to the top. You can rewrite this. And you can say x to the fifth, come on to the top here, but it's going to cause it to now have a negative power. And now instead of just being 5, it's going to be negative 5, which completely screws everything up. You cannot have negative powers on x. That's just not going to be allowed there, Pilgrim. So that's going to fail to be a polynomial. So any one term can screw up the entire thing. If I had omitted this middle term here, actually the leftovers here, if I just form them together, the leftovers would form a polynomial. That's actually a totally valid polynomial with a degree of 91 and a lead coefficient of negative pi. But that's not what we have. Some quick, interesting facts about polynomials. So as long as something fits the bill and is a true polynomial, the following facts will be true. One second. Their domain, the domain of any polynomial, is all real numbers. That's not normally true. Normally things are more nuanced. But because you're limiting the fact that you can't have negative powers, which causes division of your variable, and because you're not allowing square roots of your variable, that's really what's going to just make it so that the domain is always all real numbers for all polynomials. This is going to be a useful fact that we are going to appeal to many times. Also, if you ever do take calculus, it's useful to know that any polynomial is continuous on the entire real number line. So that's an interesting fact. And if you remember, we defined what it means to be continuous in an algebra sense, which is, remember, where it's where you could draw the function without ever having to lift your pencil and do any weird jumping of things. Well, the polynomial is going to be continuous everywhere. So that is kind of interesting. Definitely something that comes up with calculus. The range of any odd degree polynomial is also going to be negative infinity to positive infinity. And you might say odd degree, so the degree of the polynomial has to be 1, 3, 5, 7, 9. The highest power has to be an odd number. What makes that so? Well, we'll actually investigate that here in this chapter, just in the next section. But for now, we're just going to say this is true. The range of even degree polynomials is much more nuanced. In other words, there's no hard and fast rule for any one of them. All I can say is that the range of an even degree polynomial will never be the entire real number line. As much as we'd like it to be, it's just not going to be the case. But the exact range depends on the function you have. Okay, so that's just an important preamble. The reason it's important is because we are studying polynomials today. And for really chapter 3, we're talking about polynomials. We're going to start graphing these, maybe not today, but very, very soon. We're going to look at all the key points to look at on a graph, how to figure those out. So, moving on, and again, we will see some examples of synthetic division here. Zeros of polynomial functions. Now, when we're talking about the zero of a function, we're talking about what x value can be plugged into the function to produce a y value or an output of 0. What x values plug into the function and give you 0? Those are important because on a graph, those are going to be points where the function either crosses or touches the x-axis whenever you're graphing it. And so those are clearly important key points that we are wanting to cover. So here's a quick important fact that I'm going to use. For any polynomial f of x, where we've defined exactly what a polynomial is, x minus k, I'll even put it in parentheses, is a factor of the polynomial if and only if f of k equals 0. What in the world does Josh mean by that? Well, just as a quick example, x squared minus 5x plus 6. Let's look at this one. Let's call it f of x. This is certainly a polynomial. It's a second degree polynomial, which remember, we're also even going to be as bold as to call it a quadratic polynomial. What it says is that something x minus k is a factor of the polynomial if and only if you could have plugged that k value into the polynomial and gotten 0. So what I'm going to do is I'm going to show you, let's factor this guy. Let's factor it. So we need two numbers that multiply to positive 6, but when I add those numbers together, I get negative 5. Well, clearly you can see that that's going to be x minus 2 and x minus 3. So this factors as this. So now what this is saying is x minus k is a factor if and only if that k value could have been plugged into the polynomial and given you 0. So for this one, x minus 2 is a factor of the function above if and only if f of positive 2 equals 0. If I can take this value here inside the factor, plug it into the function and get 0. That's also true for this. X minus 3 is a factor of f of x if and only if f of 3 equals 0. So let's try it. Let's find f of 2. We'll plug a 2 into this function. Now the cool thing is if you plug a 2 into the factored form, you'd immediately see this becomes 2 minus 2 here, which is 0, and then it's 0 times whatever this comes out to be, which would just give you 0. So seeing it factored, that actually makes a lot of sense. But let's try it. 2 squared minus 5 times 2 plus 6. That's going to be 4 minus 10 plus 6. 4 minus 10 is negative 6. Add 6 back onto it, and you do indeed get 0. Thus, because I could plug a 2 in and get a 0, that means x minus 2 is a factor. You could also do the same for 3. If you plugged a 3 into this, it would spit out a 0. Of course, if I would have just plugged a 2 into the factored form, so maybe another way to do this. If I would just plug it into this factored form, I'd get 2 minus 2 times 2 minus 3 . 2 minus 2 is just 0, so that first thing becomes 0. That second thing can be anything at once as long as it's finite, because it's getting multiplied by 0, and that's going to make the whole thing go to 0. So that really just kind of drives this point home right here. That if you can factor it out like this, that means this principal value here can be plugged into the function and spit out a 0. In fact, that's almost kind of the whole point of factoring. That's like the whole meat and potatoes of factoring. So let's return to this thing. Important fact, for any polynomial f of x, x minus k is a factor of it if and only if f of k equals 0. I'll go one step further and I'll use some synthetic division terms we learned about last time from watching videos. This means that if I take f of x, the function itself, and divide by x minus k, I will get a remainder of 0. That was one of the major takeaways of synthetic division last time. And we will revisit this concept literally right now with an example problem. So let's see. Example is x plus 5 a factor of this polynomial x cubed plus 6x squared, x cubed plus 6x squared plus 3x minus 10. If so, what is the fully factored form of f of x? All right, so this will be our function here. This will be our f of x. The factor we're supposing is x plus 5. This means that when you write it like this, x plus 5, the k value is really negative 5. It's the opposite sign here. Because remember, when we wrote it, we said the factor has to be written like it's x minus k. Well, in order for it to appear like x plus 5, that would have to be x minus negative 5. So really the k value, if you want to think about it, it's just the opposite sign from what you see. In other words, we're going to take f of negative 5. We're going to plug a negative 5 into the original function, and if it spits out a 0, that means x plus 5 is a factor of this right here. So let's see, negative 5 cubed plus 6 times negative 5 squared plus 3 times negative 5 minus 10. We're going to have to do a little bit of arithmetic here. That's going to give you negative 125 plus 6 times 25. Ooh, that looks bad. Negative 5 squared becomes positive 25. And then that essentially becomes minus 15 minus 10. So we got a little bit of math to do. We know we need to do 25 times 6. If you do it with old school multiplication, you'll get 150. Or my scribbles, you'll get 150. So this becomes negative 125 plus 150 minus 15 minus 10. And you should see that does come out to 0. 150 minus 25 is positive 25. Minus 15 minus 10 does indeed come out to 0. So this means negative 5 is a 0 of f of x. It is an x value that can be plugged into the function that will produce a 0, that will spit out a 0. It also means that the factor x plus 5 is a factor of f of x. So when you write it as a factor, or when you write it as a 0, it's going to be the opposite sign. X plus 5 for the factor, but just negative 5 if you're talking about the 0 itself, the root. So the answer to this question is yes. Is x plus 5 a factor of that function? Yes. So now I'm going to have to erase this. But now that we know that, we know that x plus 5 will be a factor of this thing here. We need to find the fully factored form. In order to factor something, we need to take the function itself and divide by a factor. And in doing so, we can reduce it down to something that's easier to deal with. So here we're going to use synthetic division. Synthetic division is a nice way of being able to divide one polynomial by another. You can also use polynomial long division if that's something that you have used before or you're comfortable with. Then have at it, says I. But as for me and my house, we will use synthetic division. So let's set up the synthetic division. So the factor is x plus 5, but in synthetic division, you write the root itself up here in the top left corner, negative 5. Then in descending order, you write the coefficients of your function. So the coefficient of x cubed is implied to be 1 because there's nothing otherwise written. So I'm going to write the coefficients. 1, positive 6, positive 3, negative 10. And now let's do the synthetic division. We're going to realize that synthetic division is really cool, or at least really fun. I won't use that. So the first thing we do, we start with the very first coefficient and we just bring it down. So it's 1. Then we do negative 5 times 1. Negative 5 times 1 is, just negative 5. And remember, this is something we covered last time. I had you watch that video. It was only about 8 minutes long. If you did not do that, I would do that ASAP. That video can be found in the Canvas modules, the section 3.2 video over synthetic division, and it will kind of recap it. Of course, you can maybe follow my example here. So we bring down the first coefficient, then we multiply it to the term up here. Then we do 6 plus negative 5, which is going to be positive 1 again. We repeat the process. Negative 5 times positive 1 again is negative 5. Then we do 3 plus negative 5, which will give you negative 2. Then we do negative 5 times negative 2 to get positive 10 over here. And hey, thank goodness, we've got negative 10 plus 10, which is going to be 0. And this is going to be our remainder. And the one thing we like about a remainder of 0 is that means that the division was clean. That's going to mean a couple things. I'll have to just write it all out. With a remainder of 0, that means that x cubed plus 6x squared plus 3x minus 10 divided by x plus 5 is equal to, now we can read these things down here as the coefficients of a polynomial that is 1 degree less than what we started with. So we started with a 3rd degree polynomial. Now these are the coefficients of a 2nd degree polynomial written in order. So it's 1x squared, or just x squared, plus 1x, or just x, minus 2. That's what the synthetic division will tell us. Another way to express that or you can say that x cubed plus 6x squared plus 3x minus 10 can be factored as x minus 5, because we've already proven it's a factor, times the leftovers, what we got from synthetic division, x squared plus x minus 2. If you don't believe me, you can just multiply both sides by x plus 5. Basically, you're multiplying it over here. And I'm sorry, you're right, that's x plus 5. Excuse me. That's so sorry. Now, it's not fully factored because we still have a quadratic here, a 2nd degree polynomial, and maybe we could factor this one more time. The nice thing is this is going to go a lot easier. Once you have a quadratic left to factor, you already have a couple of different factoring tools. You can try just straight up factoring. We want two numbers that multiply to -2. But when I add those numbers, I get +1. And it seems like what's going to do that is x plus 2 and x minus 1. And that will indeed do it. You'll get +2x minus x, which will condense to a single x, and then -2 here. And so just lump on this x plus 5 factor. So the polynomial, the third degree polynomial, x cubed plus 6x squared plus 3x minus 10 is equal to x plus 5 times x plus 2 times x minus 1. Now let's pause for a moment. This problem had a lot of moving pieces in it. We had a lot of pieces going around here. I'll just say it right now. This section, section 3.3, is going to be the longest section we cover. I mean, it just kind of keeps going and going and going like the Energizer Bunny. I don't believe it's the hardest material we'll cover, but it definitely is the longest, and it's probably the most complex because it involves so many different moving pieces. But that's okay. We will figure it out together. Now let's talk about something called the rational roots theorem. The rational roots theorem is going to be something we use to work up a quick list of possible factors for a polynomial. So let's say I just give you a polynomial. I give you a nasty 5th degree polynomial or something like that. And I say, okay, go factor this. Well, you might look at me and say, where do I start? What do I do? And I would say, use the rational roots theorem. Use the rational roots theorem. So we'll talk about it, but really the rational roots theorem, bottom line, I'll give you the little hint here. This just gives us a list of possible roots or possible factors. That's going to be the goal of it. So I'm going to write out the rational roots theorem. It's going to look really ugly, nasty, and complicated, but then it turns out it's not going to be as bad as it looks. For a polynomial with constant p and lead coefficient q, every combination of factors of p and q that become p over q are the potential rational candidates for zeros of the polynomial. Oh boy, that's just a mouthful. That's just a mouthful. That's nice, you say. Thank you, Josh. That's really cool. So let's not get hung up on the definition. Let's look at an example of this. So let's see. Let's say you have the polynomial 6x to the 4th plus 7x cubed minus 12x squared minus 3x plus 2. So let's say you have this polynomial here. Let's work up all the possible rational roots of that polynomial. The first thing is the constant is what we're going to call P. And for this polynomial, it's 2. The lead coefficient we're going to call Q. And here the lead coefficient is 6. And it's the lead because it's attached to the highest powered term, not because it happens to be in the front. Now let's read this carefully. Every combination of factors of P and Q. So wait a minute. Let's think about what the factors of 2 are. Well, 2 is a prime number, so the only factors are 1 and 2. But actually, that's not completely exhaustive. That's not everything. 1 times 2, positive 1 times positive 2 works, but actually negative 1 times negative 2 also works. If you multiply negative 1 times negative 2, you also get that. But for the sake of keeping things simple, instead of having to write the negatives as separate factors like that, I'm just going to write plus or minus. Plus or minus 1, so positive 1, negative 1. Plus or minus 2, so positive 2, negative 2. So really that's 4 total factors. Now 6, what are the factors of 6? Well, certainly 1 and 6, but also 2 times 3 will give you 6. So there's actually going to be 4 factors initially. 1, 2, 3, 6, not the mafia. But again, negative 1, negative 2, negative 3, negative 6 also work here, which is why I gave myself space, because I'm actually going to write plus or minus in each case. Negative 1 times negative 6 gives you 6. And so on and so forth. So we've started by identifying P and Q. We've identified their factors. And now what we need to do is we need to find all possible combinations of P over Q. In other words, take every possible P and divide it by every possible Q factor. So, and this is going to be our list, and it's going to be long. Plus or minus 1, so right here, divided by plus or minus 1. And Josh has a lot to type. Plus or minus 1 divided by plus or minus 2. Plus or minus 1 divided by plus or minus 3. And so again, is this difficult? I wouldn't say it's difficult. Is it kind of a pain in the butt? Yes, it is a pain in the butt because it's cumbersome. So now plus or minus 1 over plus or minus 6. And we're about halfway there, living on a prayer, because now we have to do plus or minus 2 over plus or minus 1. We got to do this variable now, or this one. Then we got to do plus or minus 2 over plus or minus 2. Then we got to do plus or minus 2 over plus or minus 3. And finally, we got to do plus or minus 2 over plus or minus 6. Now, this expands out even further. We can simplify this even more. We're going to see that some things are going to be redundant and we can cross them out. Real quick, let's look at what it means. Raina, that's a great question. Is it still necessary to write all of them out, even if some reduce to the same fraction? That's a great question, Raina. When you're first starting out, it's nice to write them out, but we're about to do all that simplification and cross them out. So it's just kind of me being extra careful and making sure that I'm not missing anything. But if you can recognize pretty quickly that 1/3 and 2/6 will reduce to the same fraction, you never really even had to write out the 2/6 here to begin with. But I want to just kind of show you the full form of what we're doing. I want to show you the whole thing, and then I'll start crossing some stuff out. So good question. Very good question. Real quick though, let's look at what it means to be plus or minus 2 over plus or minus 6. That means there's 4 possibilities. You do positive 2 over positive 6. You do negative 2 over positive 6. So we've now taken care of plus or minus 2. Now we got to take care of the plus or minus 6 on the bottom. You do positive 2 over negative 6. And then you do negative 2 over negative 6. And you're like, Josh, I got to write out 4 possibilities. Actually, you don't, because 2 over negative 6 would just become negative 1/3. And so we've already expressed that right here, as we'll see in just a moment. Negative 2 over negative 6 would become positive 1/3, positive 2 over 6. So it's redundant. So we're gonna start seeing a light at the end of the tunnel here. Another thing, and Raina brought this up just now, well, wait a minute, these would just become different forms of 2 over 6, which we've already got here as 1 over 3. 2 over 6 obviously reduces to 1/3. So if we've got the 1/3 going down, we can get rid of the 2 over 6 completely and just deal with it over here. Another one that is going to be able to get rid of, 2 over 2 is the same as 1 over 1. It's just the number 1. So we can also cross this one out because it's redundant. It's just a repeat of this one. So I'm actually going to utilize that. I'm going to save myself a little work here. And shorten up my list here just a little bit. And so finally, this list becomes 1 over 1. So it'll become positive 1, negative 1, and I'll just write the negative 1 first. Moving down the line, negative 1/2, positive 1/2. Negative 1/3, positive 1/3. Negative 1/6, positive 1/6. Then negative 2 over 1, or just negative 2, positive 2. And then negative 2/3, positive 2/3. And now finally we're done. And all we've done is we have now found a list of all possible rational roots to f of x, to the original function. Now, to be fair, if you're pretty quick, you can kind of write up this list a lot quicker than you think. Of course, when I'm doing it in class, I have to demonstrate it, so it goes a little bit slower than it actually would whenever you're really doing it. The nice thing is there's some integers mixed in there, -1, +1, -2, +2, because what you're going to do is you're next going to be asked to completely factor. You're going to be told, hey, completely factor this polynomial here, which means you're going to use synthetic division because it's quick. You're going to use synthetic division. You're going to go through the list and you're going to keep trying to find x values that are going to give you a remainder of 0 when you do synthetic division, because then you know their roots and they can be factored out. And you're just going to keep factoring it down until you basically get it to a quadratic, and then you use quadratic factoring tools that you already know. So now we've worked up a list . Now let me just rearrange things on the screen real quick. We have this as our original function, f of x. This is a list of possible rational roots for it. So actually, let's move this even further. And this is the list we're going to work through. Now let's completely factor this polynomial. All right, so I'm just going to go down my list of rational roots. Can you do fractional ones in synthetic division? You sure can, and the math works out exactly the same. But maybe we'll get lucky. I would suggest, even though you don't have to go in this exact order, you just have to go through the list until you find something that's going to work. I would suggest using -1, +1, and if neither of those work, I would jump over, do -2, +2. And if nothing works between those, then start going down your fractions, just because you can save yourself a little bit of a headache here. All right, so let's go down the line. Let's see, -1, come on down. We're going to try the synthetic division. Now remember, if it's -1, then the factor is really x plus 1. The root, the 0, is -1, but the factor is x plus 1. Just keep that in mind. And now we're going to write the coefficients of my function here, 6, 7, give a little space between them, -12, -3, +2. Our goal is to end up with a remainder of 0. If we don't end up with a remainder of 0, then -1 is not a root of the function, x plus 1 is not a factor, and we can actually just cross it off our list completely. So remember, these are not guaranteed to work. These are our best kind of list, or our best guess, a good starting point. So in synthetic division, we start by bringing the very first term down, just bring it down as it is. Then we do this term up here times 6. -1 times 6 gives you -6. Then we add these two terms. 7 plus -6 becomes just 1. 7, it's the same as 7 minus 6. Then we keep rolling. We do -1 times +1, we get -1. -12 plus -1 is going to give you -13. Multiply again, -1 times -13 gives you +13. Add these together. -3 plus 13 is going to give you +10. Keep going until you get to the very last thing. -1 times 10 is -10. 2 plus -10 is the same as 2 minus 10, which is going to give you, well, -8. Dang. Dang. That's our remainder. It's not 0. Dang it. This means -1 is not a root of the polynomial. And also that x plus 1 is not a factor of the polynomial either. But that's okay. We got a whole list of it. Synthetic division is kind of fun, and you can't see me, but I'm doing the air quotes when I say fun because, you know, it's fun. It's fun. Sure, we'll call it that. But we know it's not going to work, so we get to take it out. It's like The Bachelor or The Bachelorette. You give it the, or no, you don't give it the red rose, right? The red rose means you get to stay on the show. Yes, I've had to watch a couple seasons of The Bachelor and The Bachelorette. Why? Because I have had girlfriends. Thankfully, my girlfriend now does not watch that. She watches Bob's Burgers. She loves that show. But I said, I will not watch Bachelor. You cannot make me.
I kind of like it.
What's that?
Moving around on it, I kind of like it.
Yeah. I mean, you know, it's fun. It's fun. I'll admit it. It's like, okay, I can watch it for entertainment, but at some point they can only do so many things. And it's just like fake human drama.
I like The Bachelor better than Bachelorette.
Well, yeah,
It has more drama than
it does. Y'all remember there was Bachelor Pad, which was just kind of a Big Brother ripoff where former Bachelor contestants would like live in the same house for a month or something, just like Big Brother. Yeah, that one was extra drama-y. That one's fun.
my wife. I kind of came around.
Yep. I used to watch some reality TV. I mean, I watched the original season of Survivor, and I was like 10 or something. That was old school. I used to think when they were voted off the island on Survivor, they were gonna go. They were gonna be killed or die or something. Because I was 10, I didn't know any better. Luckily, that's not what happened. But yeah, it was like you really do win $1 million and a lot more than that if you win Survivor. So yeah, good moment to pause because yes, we've covered a lot of ground today. Things are just moving at the speed of light. Thankfully, we're going to take probably 2 whole classes to really flesh out this section, and we should be okay. We might lose a little bit of review day. We'll have to give up part of our review day to finish lecturing, but that's okay. It's just because this section is just so long. So now we need to try +1 on our rational roots list. We'll go through, we'll just rewrite. I guess I didn't have to completely erase things from last time. I'll keep that in mind. We'll go down the list again, do our synthetic division. Synthetic division is actually kind of cheap. And it's nice because it's quick, but it only works in very, very few situations. And we can talk about it some other time. So we bring down the 6, then we do 1 times 6, you get +6. We do this, we always add these no matter what their signs are. 7 plus 6 is 13. 1 times 13, +13. -12 plus 13 becomes +1. 1 times 1 is 1. Negative 3 plus 1 is going to be negative 2. And oh, it looks like it's going to work out. 1 times negative 2 gives you negative 2. And then 2 plus negative 2 is big fat stinking 0. Yay. So now let me be explicit. We have a remainder of 0. Yay. This means 1 is a 0/root. We can use those terms interchangeably of the function. And x minus 1, the factor, is a factor of the function. In fact, this means that 6x to the 4th plus 7x cubed minus 12x squared can be written. We can take out the factor of x minus 1 that we just discovered works. And then we actually already, this is the beauty of synthetic division, we already have the coefficients of the leftovers. This is going to be, so we started with a 4th degree. Since we divided a 1st degree out of it, we're going to be left with a 3rd degree polynomial that has these coefficients, and they're written in descending order. It's going to be 6x cubed. So again, synthetic division is nice because it's really awfully convenient. But it's kind of like cheating, but, or maybe you could say it's like a shorthand method, but if it works, you know, yay. But it only works in a very, very limited or narrow window, but whatever. Now let's look at what we have. We want to completely factor this polynomial. This ain't completely factored. Get out of here. You still have a 3rd degree polynomial left over. But wait a minute, look. The p and q, p is now negative 2, q is positive 6. The p and q are basically the same. Now it's negative 2 instead of positive 2, but that's actually not going to matter. If I were to sit down and write out the rational roots of this 3rd degree polynomial in order to start working with it and being able to factor it, it would actually come out exactly the same as what we just found here. It would come out exactly the same. So the nice thing is I can now just start working with this 3rd degree polynomial to get it factored down. The negative 1, we already crossed it out for the 4th degree polynomial. So if it's not a degree of the 4th degree if it's not a factor of the 4th degree polynomial, it ain't going to be a factor of this thing either. So the negative 1 can already be crossed out. Now we found that 1 worked. It turns out 1 could work again. Just because it's worked, it can work multiple times. So we're going to go through and we're going to do the synthetic division. We're going to use this 3rd degree polynomial. We're going to use the same list, but I can still cross out this negative 1, and I might have to just repeat for positive 1. So now, here's what it's going to look like. I'm going to use a little bit of clever moving around of things. Now I'm going to try 1 from the list into this polynomial, this 3rd degree polynomial with these coefficients. So same thing, synthetic division. You're probably already starting to get used maybe to it. 1 times 6 is 6. 13 plus 6 is 19. You can probably quickly see that if signs aren't changing in here, you're always going to keep compounding and getting larger and larger. So it's probably not going to work. 1 times 19 is 19. 1 plus 19 is 20. And you can see it's not going to work. 1 times 20 is 20. Negative 2 plus 20 is 18. But that's not a remainder of 0. The remainder of 18. So now we can cross out 1. We've already fleshed it out. And we still need to factor this cubic polynomial, but we've already got the list going. Now we could start doing the fractions, negative 1/2, positive 1/2. But for the sake of simplicity, let's try these. Let's try the negative 2, positive 2. And if those don't work, then okay, we're going to have to just roll up our sleeves and do the fractions. But if they do work, we will be happy. So we're going to try -2. Remember, that's the factor x plus 2. We're going to write out these coefficients, 6, 13, +1, -2. And we're going to try them out. Just start by bringing down the 6. -2 times 6 is -12. 13 plus -12 is the same as 13 minus 12, which is 1. -2 times +1 is -2. 1 plus -2 or 1 minus 2 is -1. -2 times -1 becomes +2, and it's going to work. We've got a remainder of 0. Thus, -2 is a root of 6x cubed plus 13x squared plus x minus 2. X plus 2 is a factor of it. So we can go even further with it. We've got x minus 1 here. And we can actually get rid of all this now. And then we said x plus 2 is going to be a factor. And actually, I should not have erased that. Whoops. Sorry, I don't have a good memory. There it is. Okay. X plus 2, we just factored it out. And the leftovers, we started with a third-degree polynomial. We're down to a second-degree polynomial or quadratic polynomial. The leftovers are 6x squared plus just x minus 1. And now I can get rid of this. And now we're almost done. Now we have this quadratic. Technically, the rational roots test, you could drum up a new list of rational roots for this. But if it's a quadratic, we already have strategies for factoring this one. So let's try factoring the old school way. 6 times -1 is -6. Now we need two numbers that multiply to -6 but add to +1. And it looks like 3 and -2 are going to do that. But because the lead coefficient isn't 1, we're going to have to use factor by grouping. Or if you have a factoring method that you're already comfortable with, then I say, let it be. I will not overcomplicate things. And so this should be something you're comfortable with now. There's group 1, there's group 2. The GCF of group 1 is 3x, leaving you with x plus 2 left over. Or I'm sorry, x plus 1, excuse me. No, excuse me. No, I don't know what I'm saying. 2x plus 1. Now, since these are both negative, you might want to factor out a -1 and just call that 2x plus 1 over there. And then finally, I can factor out 2x plus 1. I'm left with 3x minus 1. Now, if you could have factored 6x squared plus x minus 1 and you already had a system that worked for you and you're happy with it, then don't overcomplicate things. This is called the factor by grouping method. And so finally, the fully factored form of 6x to the fourth plus 7x cubed minus 12x squared minus 3x plus 2 is this business plus, in addition, the x minus 1 and x plus 2 factors we'd already taken out. Ta-da! So this is the fully factored form of this original fourth degree polynomial. And it makes sense according to that fundamental theorem of algebra we talked about. You have 4 different unique factors and you have a fourth degree polynomial. So it's just kind of confirming maybe a few things we already knew. The very last topic we'll talk about, multiplicity. And I'll just go ahead and define it. The multiplicity of a factor is how many times it shows up in the factored form of a polynomial. Multiplicity is also a Michael Keaton movie from the early 90s where there's like 5 of him or something. It's a pretty corny movie. And you know, this is when he was still doing Batman, so I don't know why he did that movie. It was another time. A quick example of multiplicity is, let's say you have a polynomial that's fully factored like this. And it's going to be a long one. Let's say this is the fully factored form of a polynomial. Look, the factor x minus 2 shows up 1, 2, 3, 4 times. In fact, you can use just exponential, since all these are just being multiplied together. That's just x minus 2 to the 4th power. X plus 3 shows up twice, so that's just x plus 3 squared. X plus 7 shows up just once. So that's just x plus 7. You could say to the 1st power, but you don't have to. So this says that the factor x minus 2, which is the root k equals 2, has multiplicity of 4. And this factor has multiplicity 2. This factor has multiplicity 1. Okay, that's it for today. We will pick back up on this on Tuesday.